Hi everyone. So today's PowerPoint is going to introduce the topic of what we mean by electrical resistance and one of the most important equations that you'll use all the way through your physics career called Ohm's law. Before we start, a quick reminder that when you're drawing electrical circuits, then obviously in physics it's much easier to use symbols. So you need to be aware of all of these symbols, and there's some more that you'll need to kind of pick up on a bit later on in the course, but these are the kind of standard symbols that you've used already probably. So they'll be in the notes when you come to do that. So first of all, what do we mean by resistance? So the resistance of a material, electrical resistance of a material, is a measure of the opposition to the current flowing through the material. So basically, all materials have got some kind of resistance. They will stop or try to stop the current flowing through the material. And we have a measure of it, which we'll talk about in this PowerPoint and later on as well, which resistance is measured in a unit called ohms, or you can have that the Greek letter omega for short. So you can write out the word ohms like that, or the symbol, the Greek letter omega. So for most materials, the resistance depends on a number of things about them. So the first one would be what type of material it is. So basically, better conductors have got a smaller resistance, which kind of makes sense. So the smaller opposition to the current, then the more current you get. So therefore they're better conductors. So for example, all metals are better conductors than non-metals. In fact, non-metals are generally going to all be insulators. Now, when we're talking about the length of material, then like if you've got a length of wire, for example, then the longer the wire, then the greater the resistance, and conversely, the shorter the wire, the shorter the resistance. The thickness of the material. So thinner materials have actually got a higher resistance. So if you imagine trying to push electric current through a thin wire, it's going to be more difficult than pushing it through a thick wire. The analogy that sometimes is used, like putting water through a hose. If you've got a small thin hose, then the water won't come out, won't flow through the hose very well. But if you've got a big thick hose, then the water will flow through the hose. Get kind of tongue-tied there a wee bit, not to worry. And then this last one isn't always the case, but in general, higher temperature materials have got a higher resistance. Now that's going to be an extension thing that we'll look at some point down the line. So first of all, we're going to talk about an experiment that obviously we can't do very easily. There are various YouTube clips and various places where you'll find these experiments carried out, but for me, we're just going to look at the experimental setup. So here we have a very simple circuit. So we've got a variable voltage DC supply. That just means that we can change the voltage of the supply there. We've got, this is a symbol for a resistor, and we've got our voltmeter connected in parallel across the component, and we've got an ammeter there to measure the current going through the resistor. So we can set up this circuit to investigate, and what we want to do is change the voltage of the DC supply and measure the current and voltage, or potential difference as we should now call it, I suppose, for various points. Then we plot a graph. And in this case, the graph is of voltage, which is on your y-axis, against current on the x-axis. And what you find is you get a straight line graph through the origin. Now that is an extremely important graph to have in physics, because that's how we prove relationships. If you plot points of any two things against the other thing, then if you get a straight line graph through the origin, then that proves something, that shows something. And what it shows is that the voltage is directly proportional to the current. So to read that out more fully, the voltage across the resistor is directly proportional to the current through the resistor. Now this is all dependent on keeping the temperature constant, because as the temperature changes, so if you have too big a current, then that will affect the temperature of the resistor, and then that will affect the graph as well. But for small voltages and currents, then this graph shows that the voltage is directly proportional to the current. So mathematically, we can write that as a mathematical thing rather than in words. So V is directly proportional to I, that's what we've just said there. And we can write that in symbol form by saying that V, and then that symbol there, which is the Greek letter alpha, is proportional, is proportional to. So this means the same as that in words. So V is proportional to I. Now we can rearrange that in various ways to give us that the V over I equals a constant. And that constant is equal to the resistance. So remember we spoke about the resistance earlier on. So therefore that now is a mathematical thing that we can actually calculate. And therefore also I've added on in the graph there that if you work out the gradient of that line, the voltage against current graph, then the gradient of that line also equals the resistance. So we can then rewrite that as a mathematical equation, which would be that resistance, which is capital R, and it's measured in ohms, equals the voltage or potential difference in volts divided by the current in amps. So that is a version of what we would call Ohm's law. So V is the potential difference in volts, I is the current in amps, and R is the resistance in ohms. Now Ohm's law, as it's known as, is usually written in terms of V equals IR. That's the way it will show up on your formula sheet during any exam. So what we're going to do is we're going to work our way through some worked examples. First couple of ones will be quite straightforward, and then they'll move on to be a bit more complicated, which I've deemed to be extension work. All of this first lot of stuff will be core work. So the question we've got is we've got a current of 0.015 of an amp in an LED, light emitting diode. The LED has a resistance of 120 ohms. Calculate the PD across the LED. So the normal procedure, as always would be, first thing you do is you write the information from the question along with its correct symbol in the left, ideally in the left-hand side of the page. It doesn't really matter where you put it, but you write it down. Because when you've written down I, R, and V, then obviously there's a whole stack of equations you're going to need to be able to use by the time any exam comes along. So therefore this is going to point you towards, hopefully, V equals IR. So then the next stage is you write down the correct equation, which is, funnily enough, V equals IR. You then, next thing you do is you substitute in the numbers. So you replace the symbol for I with the number 0.015, multiply it by the resistance of 120 ohms, and then you write the correct answer, hopefully with the correct unit. And this would be what we would call a standard 3-mark question. So you get 1 mark for selecting the correct equation, 1 mark for substituting in the numbers correctly, and then 1 mark for the correct answer. And don't forget about the unit, because you will lose the whole of that last mark if you don't write in the correct unit. Okay, question 2 is similar, just different numbers, and we're going to, this time we're not going to try and find the voltage, we're going to try and find the current. So we've got the kettle connected to a 230 volt supply, so that would be main supply voltage switched on. The element of the kettle has a resistance of 25 ohms. So first of all, again, we write down the information with the correct symbol. So in this case, we've got V and R, but we want to find I. So same as the last one, you write down the correct equation, correct relationship. Substitute in the numbers. Now, there's various methods you can use. I'm just going to show you this one just now, that where you substitute in the numbers in the correct place. So we've got 230 equals I times 25. And then with a fair bit of practice, and you've done a lot of this with speed, distance, time, and various other equations, you should be able to recognize how to rearrange that, which would be that the current I equals 230 divided by 25. So you want to divide that side of the equation by 25 to get I on its own, and then you write it the other way around, and it gives you that the current is 9.2 amps. Again, standard 3 marker, 1 mark for that, 1 mark for that, 1 mark for the final answer. So the last question, I've said this is extension work because in a lot of cases the voltage, the current and the resistance won't be in volts or amps or ohms, that might be in kilovolts or megavolts or milliamps, microamps, etc., etc. So this makes it a wee bit more difficult and something you have to remember to do. So that's why I've deemed this to be the extension work, but it's something you will all have to do. So there, just to remind me there that the question, the potential difference is in kilovolts. So the power supply is a voltage of 2.4 kilovolts. So you have to obviously remember what kilo stands for, that's times 1,000. And the current is 16 milliamps. So we need to change the milliamps into amps as well. So the easiest way is, well, 2.4 times 1,000 gives you 2,400. Now for the current, it's going to be 16 divided by 1,000. But you should all be aware and able to use scientific notation. So it's easier to write down 16 times 10 to the minus 3 is the current in amps. You don't need to change that into a number between 0 and 9.9. It's okay in physics, we'll let you away. We're just writing 16 times 10 to the minus 3. And in this case, we want to find R. So again, it's a VIR. So the correct equation is Ohm's law, V equals IR. Substitute in the numbers. So we've got 2,400 equals 16 times 10 to the minus 3 times R. So you want to get R on its own. So you're going to move the 16 times 10 to the minus 3 and divide it over here and then write the thing round the other way, if that makes any sense. So your next line would be R equals 2,400 divided by the 16 times 10 to the minus 3, and that gives a resistance of 150,000 ohms. And so these type of questions are a bit more tricky, and you have to know your prefixes, which we have already covered, but maybe worth reviewing and going back over. So that's the PowerPoint finished. It will be posted online, and then you can use this, and there's some questions I'm going to pose for you, and then later on in the week there'll be a Teams quiz to complete. But basically Ohm's law is a very important part of the course, and there's like a whole stack of questions you can do on this. So practice makes perfect. So good luck with all of that, and I'll catch you next time.